that one, don't want that. Okay. Okay. So the distribution we're going to talk about right now, I'm skipping this stuff, don't worry about it. The distribution we're going to talk about right now is called the normal probability distribution. It's got a couple different names. The common name that a lot of people know it by is the bell curve. Who here has ever heard the phrase bell curve? Bell curve. Okay. So a couple people have heard this. You may or may not know what this is. What we're going to do right now is take a look at what this is. I'm going to start with what I hope is an interesting example. What's going on here? What we've got is balls dropping from always the same place. Yes, absolutely. This is like a common carnival game. Okay. So you've got balls being dropped all from the same place. And what happens to the ball? Right, there are all these pegs here, and the ball has to bounce off of them, and eventually it bounces, and falls to the bottom. So my question is, when the balls fall to the bottom, are they going to make a flat pile? Is the pile going to be flat going across? No? Why not? Where are the balls more likely to fall? Well, they're all going to fall to the ground. The balls are most likely to fall in the middle.
But that's saying that if you're dropping all the balls.
Yeah, well, we're dropping all the balls from exactly the same spot.
Yeah.
Right.
Well, yeah, they're going to fall in the...
Okay. Because think about it. What would have to happen for the ball to go all the way to the left? Every time it bounces, it would have to bounce left, 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 left. Is that very likely? No, it's more likely the ball kind of bounces left, right, back and forth. And that would put it back in the middle. Same thing for bouncing to the right. So it's much more likely that it just kind of bounces around and lands in the middle. So the question is, what is the pile on the bottom going to actually look like? Irene? It's going to look kind of like a mountain, absolutely. So it turns out that the balls will form a very specific shape. And that shape is this black outline that you see here. And that black outline is called the bell curve, or the normal distribution. Now this is, and you can see, because this is an experiment, it won't work out exactly right, because I'm talking about individual balls. But if we were to drop, say, 1 billion balls, they would fall in this shape. Okay, and you can see this one's pretty close. Now, it turns out that there was a formula for this curve, for this graph. It's very complicated. We're never going to look at it. All right. But I want you to get the intuitive understanding of where this curve comes from. The idea that it's much more likely to be in the middle, and it's relatively rare to be out near the left end or the right end. That's the idea. Okay? So let's try to understand some things about this normal distribution, which you can also call a bell curve. So first of all, what is the area underneath the curve? The total area underneath the curve. It has to be 1. Why? Yes, because area is the same as probability, and total probability is 1. So total area is 1. That's one of the most important. All values are from 0 to 1. It's symmetric. That sort of makes sense from the experiment I just showed you, and it sort of looks symmetric, but I'm just telling you, definitely it is symmetric. Okay. Now, which value, or where's the value which has the highest frequency?
In the middle.
In the middle. Now, what do we call the number with the highest frequency? Most common number is the mode. So the mode is in the middle. Now, the median. What's a median? The middle number. Where do you think the median is? In the middle. Specifically where I've drawn this dotted line. Now, why does it make sense that the median is right there? Right. It's the middle because, what do we know about this? It's symmetric. So if you like, think back to when we said you can find the median by crossing off one number on the left, one number on the right, and keep repeating that until you get one number left. Well, because it's symmetric, clearly, relative to where I've drawn this dashed line, there are the same number of data values on the left side of that as there are on the right side, because it's symmetric. So the median will be exactly in the middle of this dashed line. And I hope that it also makes sense, even if we can't necessarily prove it, that where do you think the mean is? The mean is also in the middle. So hopefully that just seems to make sense. Okay. So we understand a little bit about this. I want to start talking about the normal distribution and numbers. How do we start counting and measuring things? Well, like as we've always talked about before, this represents a distribution of data. So I want to talk about a specific set of data. The normal distribution, I need to say this. One of the reasons that the normal distribution, the reason that we study it, is not because it's easy to study. It's the mathematics behind it is very complicated. We're not actually going to do it though. We'll have some other techniques. But the normal distribution is very, very, very common. There are many, many things that you can study where if you collect your data, you would find that they have a normal distribution. Or if you were to plot your data, you would get something that looked like a bell curve. Heights are one of these things. If you were to take a survey of a big population and record everyone's height, you would get something that looked like a bell curve. If you were to plot people's weights, you would get something that looked like a bell curve. If you were to plot people's IQs, you would get some your distribution would look like a bell curve. Many, many, many things, when you plot the data, it looks like a bell curve. So this is a very, very important distribution. I want to look at one example of this. So let's talk about male heights. Now when you talk about the normal distribution, there are two things that you need to know in order to fully understand it when you're talking about data. One thing you need to know is the mean, and you also need to know the standard deviation. We'll see why as this goes forward. Now for men, I'm going to say the mean mu is 68 inches, and I'm going to say the standard deviation is 2 inches. Those are approximately correct. I rounded them a little bit.
Where did you get them?
I estimated. Okay. Now, let's start labeling our distribution picture. What is one number that we can write down right away? 68. Where does 68 go? In the middle. Awesome. And just so we remember, 68 is a data value. So I want to remind myself that these are really that I'm writing down x values. Now, one way to write one thing that you could do is write down along the horizontal axis. You could write down all your data. You could write down 68, 69, 70, 71, da da da. Turns out there's going to be a better and more useful way to label this picture. The better and more useful way to label this picture is by counting by standard deviations. We'll see why by the end of today. Now, 68 is the mean. What is the height that is one standard deviation above the mean? Yes. Because the standard deviation is 2. So 2 above that is 70. What's the height that is 2 standard deviations above the mean? Yeah, 72. And what male height is 3 standard deviations above the mean? 74. Okay. Now similarly, we can go the other way. What male height is 1 standard deviation below the mean? 66. 2 standard deviations below, 64, etc., etc. Okay. Now, I want to remind you, we have already learned of a way of something of how we count standard deviations. And what's that called? The Z-score. Absolutely. So we're going to see starting today why the Z-score is so important. So, what does Z-score mean in words?
The value.
Which value? Exactly. That's what a Z-score is. It's how many standard deviations you are from the mean. So for example, for 70, what's the Z-score? The Z-score was 1. It was 1 standard deviation above the mean. And I want us to think of these two things simultaneously. So next to all my x values, I'm going to write down the Z-scores. And again, to make sure we know which is which, I'm going to label this row Z. Now for 72, what's my Z-score? 2. And for 74, what was my Z-score? Okay. And like similarly, the other way, what was the Z-score for 66? Yeah, it's -1. And what's the Z-score for 64? -2. Now what's the Z-score for 68? It's 0. Absolutely. Because remember that the Z-score measures how far you are, how far away from the mean are you. Well, 68 is the mean. So, how far away is it? It's 0. Sorry? In a sense, yes. Absolutely. Okay. So, what is the Z-score for a male height of 72 inches? Now, this seems like a silly question. We just wrote down the answer. But what I want to remind you of is that we have a formula for calculating Z-score. What is the formula for calculating Z-score? Okay. So x minus mu over sigma. But I also want you to remember it in this way. X represents your data value. And what does mu represent? So it's the data minus the mean divided by standard deviation. Okay. So in this case, what are these? How does with the numbers? Exactly. 72 minus 68 over 2, which gives you 4 over 2, which is just 2. So the point here is that it's all connected. There's a connection between how we label our picture and doing these calculations. And everything should agree. Okay, next. Equal time. Let's do the same thing for female heights. Now for female heights, I've got these estimates where the population mean is 64 inches and the standard deviation sigma is 1.5 inches. So let's go ahead and make the same chart for female heights. So what's the first number that I can label? Which goes where? In the middle. And again, what kind of value is 64? It's a data value, so how does that get labeled? These are x values. Okay. So one standard deviation above is 65.5. Two standard deviations above is 67. Plus 1.5. Three standard deviations above is 68.5, etc., etc. We can also go the other way. One standard deviation below would be what? It's 62.5. Check it out. Okay. And once again, let's also label z-scores. So what's the first z-score we can put down immediately, easily? Right. So what's the z-score?
-1.
What's the easiest z-score to always put down?
0.
And where does that go? In the middle. Yes. Okay. Then the z-score for 65.5 was 1, for 67, 2, for this is 3. Going the other way, -1, etc. Comparing these two pictures, what do you notice about z-scores? Z-scores are always in the same place. Okay. So, for that reason, I'll come back to this question in a second. For that reason, when you talk about a normal distribution and you're only using z-scores, you call it the standard normal distribution. Because the z-scores are universal, they're universally in the same place in your distribution. So how does something like using z-scores and saying standard normal distribution, how does that help? Well, here's a sort of question that we saw briefly before. I'd like to revisit it. If you have a man who is 70 inches and a woman who is 67 inches, who is taller? Well, it depends what you mean by taller. Who's taller in inches? The man. That's obvious. That doesn't even require any thought or calculation. But that's not really a fair comparison. It makes a lot more sense to ask who is taller for their gender. And so how would you then make that comparison? Compare z-scores, absolutely. So for the man, what's the z-score? Let's do it using the formula. 70 minus 68 divided by 2. That's 2 over 2, so the z-score is 1. What about for the woman? What's the z-score? 67 minus 64 divided by 1.5. That works out to 3 over 1.5, and that's 2. So relatively speaking, who's taller? The woman is taller. Okay. So again, that's why z-scores, we like to call it the standard normal distribution, and this is the value of z-scores, is that it gives you a universal way of comparing things which otherwise it's not really fair to compare directly. So there's one important question which we haven't asked yet, which is we talked around it but haven't really asked this question, which is how do you find probabilities using the normal distribution? This is clearly not a rectangle. And again, finding probability is the same as finding the area. Now, this is not a rectangle. So if I just said find some area, it would be very hard, and for you at this point, impossible. You certainly can't look at that picture and say I can say what the areas are. So what we're now going to do is build up a way to find the areas, which is the same as the probabilities. So first, I'm going to give you a little cheat sheet. Using z-scores, and I've written it in percents to make it a little more user-friendly. The probability of being for a z-score to be between 0 and 1, or the percentage of the data that's between 0 and 1, is 34%. This is the nature of the normal distribution. The probability for the z to be 1 and 2, or the percentage of your data between z equals 1 and z equals 2, is 13%. Between 2 and 3, you have 2%, etc., etc. So, where do these percentages, or where do these probabilities come from? Fancy calculations. And by the end of the period, we're going to see how to actually start getting numbers in our, and probabilities in our own way. Now, statisticians are also concerned with asking another sort of question. What's the probability of being within one standard deviation of the mean? Now, what does it mean to be within one standard deviation of the mean? You could be as low as what? In terms of z-scores, you could be as low as what? I heard someone say it. Okay. Well, no, 0 is the mean. But we're saying up to one standard deviation away. Could be as low as -1 and as high as 1. So what's the probability or percentage that is within one standard deviation? %68. And there you go. Similarly, we could ask, what's the probability of being within 2 standard deviations of the mean? And that means going as low as and as high as 2. And that probability, if you add them all up, you get 95%. Or a probability of 0.95. And then you can also ask within 3 standard deviations of the mean. And that's z from -3 to 3, and for that you get 99%, or probability of 0.99. Okay. So using just this, I like to call this the little cheat sheet, you're going to already start to say some very interesting things. For example, what % of men are between 68 inches and 72 inches? Well, where was 68 inches? We have to remember where was 68 and where was 72. Where was 68? Yeah. In the middle, so the z-score is 0. And for 72, the z-score is 2. So let's go back to our little cheat sheet. So that's really the same as having a z-score between 0 and 2. So what's that percentage or probability? Right. You could say either 47% or 0.47. So notice we can already say some really powerful things just using these simple numbers. Now I'd also like to take this last problem and write it out in notation. So first of all, one way to say this is the probability that a man is, or a man's height is between 68 inches and 72 inches. The probability is 0.47. How can we write this out in notation? What's the first thing we write down? P. So it's P, 68 less than X less than 72. And we just calculated this. What is it equal to? This is 0.47. Now, notice that asking this question, saying that the height is between 68 and 72, is exactly equivalent to asking what? Hint, it's about z-scores. This is exactly finding the probability that x is between 68 and 72 is exactly equivalent to finding the probability of what? Hint, stated in terms of z. A z-score between 0 and 2. Exactly. Because when x is 68, what's the z-score? And when x is 72, what's the z-score? 2. So these are exactly the same. In this problem, these are exactly the same thing. Does that make sense? Okay. So again, I just gave you a quick little idea of a couple different percentage or probability figures. Naturally, we want to be able to do these calculations for something other than just z as an integer. And that's what we're going to talk about right now.